So today we're here to learn about Wilson's theorem. In 1770, an English mathematician, Edward Waring, in his Meditations Algebraic, announced several new theorems, and one of his students, John Wilson, says if p is prime, then p divides p minus 1 factorial plus 1, or p minus 1 factorial plus 1 is equivalent to 0 mod p, or p minus 1 factorial is equivalent to negative 1 mod p. And the first proof of Wilson's theorem was given by a French mathematician, Joseph Lagrange, on 1771. The mathematician after whom the theorem named John Wilson conjectured but did not prove it. Theorem. Wilson's theorem. P minus 1 factorial is equivalent to negative 1 mod p if and only if p is prime. We have 2 minus 1 factorial plus 1 equals 2. Since 2 minus 1 equals 1 factorial and 1 plus 1 is equals to 2. 3 minus 1 factorial plus 1 equals 3. 4 minus 1 factorial plus 1 equals 7, and so forth. For example, we have p is equal to 2. So we have 2 minus 1 factorial equals 2 minus 1. 1 factorial is equivalent to negative 1 mod 2. Or equal to 1 is equivalent to negative 1 mod 2. Then 2 divides 2, therefore p is equals to 2 is correct. If we have p equals to 3, 3 minus 1 factorial is equals to 2 factorial. That is equivalent to 2 times 1, equivalent to negative 1 mod 3. And 3 divides 3, therefore p is equals to 3 is correct. If p is greater than 3, suppose a takes any value from 1, 2, 3 until p minus 1. Assuming that a is any value but a positive integers. So we have ax is equivalent to 1 mod p, where a and p is equal to 1. Therefore, ax is equivalent to 1 mod p has a unique solution, or it can be read as a factorial. A times a prime is equivalent to 1 mod p. Therefore, a prime is greater than or equal to 1 but less than or equal to p minus 1. And a is greater than or equal to 1 but less than or equal to p minus 1. So we have here Theorem 1. If p is prime, then p minus 1 factorial is equivalent to negative 1 mod p. Suppose that p is equal to 7. And by Wilson's theorem, 6 factorial is equivalent to negative 1 mod 7. Writing out the terms of 6 factorial and the congruence, we have 6 times 5 times 4 times 3 times 2 times 1 is equivalent to negative 1 mod 7. And from the theorem, we have 6 times 5 times 4 times 3 times 2 and 1 have an inverse modulo 7. Since all are relatively prime to 7, and we have 1 squared that is equivalent to 1 mod 7, and 6 squared that is equivalent to 36 and equivalent to 1 mod 7. Therefore, since the 4 terms left we should be able to match them up as inverses of each other. We see that 5 times 3 is equivalent to 1 mod 7, and 2 times 4 equivalent to 1 mod 7. Therefore, rearranging the terms of 6 factorial. To put inverses to next to each other, we have 6 times 5 times 3 times 4 times 2 times 1 is equivalent to 6 mod 7. And 6 minus 7 mod 7. 6 minus 7, we have negative 1 mod 7. Negative 1 mod 7. So same with our answer, 6 factorial, that is equivalent to negative 1 mod 7. Notice that 6 is its own inverse modulo 7 because 6 times 6 is equivalent to 36, that is equivalent to 1 mod 7. In fact, for any modulus p, the value of p minus 1 is always its own inverse modulo p. And here, for each value of p, find the least residue of p minus 1 modulo m. For example, p is equals to 4. So we will substitute 4 into p. We have 4 minus 1 factorial, that is equivalent to 3 factorial. 3 factorial, or 3 times 2, is equal to 6, that is equivalent to 2 mod 4. We'll find the value that is divisible to 4 nearest to 6. So we have 4 times 1, then 6 minus 4, we have the remainder 2. That's it. So another example, for example, p is equal to 5. So we will substitute p into 5. We have p minus 1 factorial, substitute 5. We have 5 minus 1 factorial, that is equivalent to 4 factorial. 4 factorial, 4 times 3 times 2, that is equal to 24, equivalent to 4 mod 5. Since we'll find a number that is divisible by 5 nearest to 24, so we have 4 times 5, then 24 minus 20 is equals to 4, so 4 is the remainder. Then we have 4 mod 5. Hello! So since we're done talking about the Wilson's theorem, and now we'll proceed to the Chinese remainder theorem. I have here given modulus. I have x that is equivalent to 3 mod 5. That means that x has a remainder of 3 when divided by 5. Then x is equivalent to 1 mod 7. That means x has a remainder of 1 when divided with 7. Then x equivalent to 6 mod 8. That means x has a remainder of 6 when divided by 8. So when can we say that we can use a Chinese remainder theorem with the given modulus? So the Chinese remainder theorem works here. It's because the given modulus are relatively prime. Look at mod 5 and 7. And we know that 5 and 7 are prime numbers. And prime numbers are numbers that has no other factor or highest factor but 1 and itself. Again, here we're going to use Chinese remainder theorem. It's because the given modulus are relatively prime. So, for example, we have x equivalent to 1 mod 3, x equivalent to 1 mod 4, x equivalent to 1 mod 5 and x equivalent to 0 mod 7. Look at these given modulus. So we can see that their number 3, 5, and 7 are prime numbers. So we can use Chinese remainder theorem in finding the value of x from the given modulus. After that, we'll find the value of the modulus, which are 3, 4, 5, and 7. We'll multiply 3, 4, 5, and 7 to get the value of m, or the modulo. So we have 3 times 4 times 5 times 7, that is equal to 420. So our next step, we'll find values of modulo 1, modulo 2, modulo 3, and modulo 4. To find the values of modulus 1, 2, 3, and 4, you are going to multiply each modulus except for its own modulo. We have here for m1, you're going to multiply mod 4, 5, and 7. So we have 4 times 5 times 7 is equal to 140. For modulo 2, we'll multiply mod 3, 5, and 7. 3 times 5 times 7, that is equal to 105. So for modulo 3, we'll multiply 3, 4, and 7. We have 3 times 4 times 7, that is equal to 84. For modulo 4, we'll multiply 3, 4, and 5. 3 times 4 times 5 is equal to 60. Our next step is to find the values of y1, y2, y3, and y4. That is equivalent to 1 mod. We'll copy the given modulus. We have mod 3, 1 mod 4, 1 mod 5, and 1 mod 7. To find the values of y1, y2, y3, and 4, you are going to find a number that is divisible by 3 but less than 140. So we have 3 times 46, so we have 138. Then 46 times 3 is equal to 138. 140 minus 138, we have 2. So the remainder is 2. We'll put 2y1, that is equivalent to 1 mod 3. For y2, we'll find a number divisible by 4 but less than 105. So we have 26. 26 times 4 is 104. Then 105 minus 104 is 1. So the remainder is 1. So we will put 1 y2 is equivalent to 1 mod 4. For y3, we'll find a number divisible by 5 but less than 84. So we can have 16 because 16 times 5 is 80. So 84 minus 80 is 4. So we'll put the remainder. We put 4 y3, that is equivalent to 1 mod 5. For y4, we'll find a number divisible by 7 and less than 60, so it's 56 because 8 times 7 is 56. Then 60 minus 56 is 4, so we have 4. We'll write 4 y4, that is equivalent to 1 mod and 7. That was it. Then find values of y1, y2, y3, and y4. So for y1, that is equal to 2. It's because 2 divided by 2 is 1, and nearest to 3. For y2, we have 1, because 1 divides 1 is also 1. For y3, we have 4, because 4 divided by 4 is 1, and 5 minus 1 is 4. For y4, that is equal to 2. And now we have all our inputs to find the value of x. To find the value of x, we'll write here x equals 2. We'll get first here the remainder of the given modulo, which is 1. Then the value of m, 140, and our y1 here. So we'll multiply the 3. We have 1 times 140 and 2. Then add the second modulo, plus 1 multiplied to m2, 105, and y1, which is 1, plus the third modulo. The remainder is 1. We write here 1 times modulo 3, which is 84, and times y3, we have 4. Plus, then if we multiply 0 to any number, then the answer is 0. So we'll just write 0, the remainder, 0 times 60, m4, and y4, which is 2. Then we'll simplify. 1 times 140 times 2 is equal to 280, plus 1 times 105 times 1 is equal to 105, plus 1 times 84 times 4 is equal to 336, and any number multiplied to 0, that is equal to 0. We have 0. And now we will add 220, 105, and 336. We have 721. And since we have here the values of all modulos, if it will be multiplied, we have 3 times 4 times 5 times 7, we have 420. So we will subtract 420 to 721. I have here 721 minus 420, that is equal to 301. And 301 is our value of x from the given modulos. And that was about Chinese remainder theorem, and I hope you're learning. And for the next topic, we have the Euler's theorem. For its definition, let n be a positive integer. The Euler phi function, or phi function of n, is defined to be the number of positive integers not exceeding n that are relatively prime to n. And for the example, we'll find positive integers not exceeding to n that are relatively prime to n. So let's say n equals 1. Since the only positive integer not exceeding to 1 and relatively prime to 1 is 1, so phi 1 is equal to 1. For example, we have n equals to 2, and the only positive integer not exceeding to 2 and relatively prime to 2 is 1, so we have phi 2 equals 1. We'll count numbers of positive integers that are relatively prime. For example, we have n equals to 3. Then the numbers of positive integers not exceeding to 3 that are relatively prime is 2 and 1. So we have phi 3 equals 2. And if we have n equals to 4, we will count the number of positive integers not exceeding to 4 and relatively prime to 4. So we have 3, 2, and 1. We have phi 4 equals 3. We'll have here 35x equivalent to 47 mod 24. What we're going to do first is to reduce to its least residue. We'll find a number that is divisible by 24 but less than 35. So we have 24, then 1 times 24 is 24, 35 minus 24 is 11. So we'll write 11x, then least residue, we have negative 1 mod 24. At this point, we can't solve this modulo directly because we'll use the Euler's theorem. And to use the Euler's theorem, we will take then 11 and 24. And since 11 and 24 are relatively prime, we'll use the Euler's theorem. So we'll find 11 phi of 24. That is equivalent to 1 mod 24. First, we'll find phi 24. For phi 24, we'll make two adjacent parentheses. For its factors, we have phi, then parentheses, and phi, parentheses. We'll find a number or factors of 24 that are relatively prime. So we have 8 and 3. So for 8, we will find positive integers not exceeding to 8 and relatively prime to 8. So we have 4 numbers. We have 1, 3, 5, and 7. So for 3, we have 2 and 1. So we have 2 positive integers that are relatively prime. We have 4 times 2. 4 times 2 is 8. Therefore, 11 phi 24 equals 11 to the power of 8. Then we have 11 to the power of 8 is equivalent to 1 mod 24. And we will proceed here. Since we know that the rule in multiplying exponent will add their exponent if it has the same base. So we have here 11 to the power of 1. Then we'll substitute 11 to the power of 8. So we have 11 to the power of 7 times 11x equivalent to negative 1 times here 11 to the power of 7 mod 24. Next, 11 to the power of 8 is 1. So we have x equivalent to negative 1 times 11 to the power of 7 mod 24. And after that, we'll find a number equivalent to 1. So if we have 11 to the power of 2 equivalent to 121, that is equivalent to 1. We have x equivalent to negative 1, then substitute 11 to the power of 2. We have 11 to the power of 2 times 3. Since 2 times 3 is 6 times 11, and exponent here 1. So we have 11 to the power of 7. Copy mod 24. There we have x equivalent to negative 1. Then our 11 to the power of 2 is 1. So we will change 11 to the power of 2 into 1. We have 1 to the power of 3 times 11 mod 24. Next, simplify. We have x equivalent to 1 to the power of 3 is 1. So we have negative 1. Negative 1 times 11 mod 24. We have x equivalent to negative 1 times 11. We have negative 11 mod 24. And we'll have 24 minus 11, we have 13 mod 24. So this is our modulo. X equivalent to 13 mod 24. And that's the way on how to use the Euler's theorem following phi here, phi or phi that was the same as phi. And I hope you have learned something. Thank you.